All right, 15.2, we're going to encounter a name that we have seen before. Do you remember how to pronounce E-U-L-E-R? No. It's Euler. It's Euler. These are Euler circuits. We saw Euler diagrams back when we were doing the Venn diagram section. Do you remember that? And truth tables. Actually, that's when we were doing truth tables. One section was about Euler diagrams. Well, this is Euler circuits. Okay. So Euler was a mathematician, and he did work in different branches of mathematics. So we're encountering a couple of them. All right. The first couple of things we're going to talk about. You've seen these before, but not with the word Euler in front of them. Okay. You've seen paths and you've seen circuits, and we talked about paths actually having this property that we don't repeat any of the edges. That was what a path was, and the circuit being the idea that we don't repeat the edges and we return to where we started. Well, an Euler path and an Euler circuit have the feature that we actually cross over all of the edges. Okay? So not just do we not repeat anything, but we don't miss anything either. Do an example, and unfortunately, because the directions are not the directions, but the components of the problem are so long, it's on two different screens here, but it's on one on your paper, so you can see it all at the same time. We've got a graph. Looks like this, something like this anyway. And it says, consider the following graph. Which of the following are Euler circuits for the graph? And if they're not an Euler circuit, why not? So the first one that you have, which is written here on the next screen if it wants to turn. Really? All right, look at it. The one that you have on part A is what? Can somebody read it to me? Okay, so first question is it a circuit? All right, A to B to E to D to A. That's what Tyler told me. First, is it a circuit? So remember, what it means to be a circuit is it starts and ends in the same place, and you can actually cross through edges that represent this diagram. So can you really go from A to B? And then can you go from B to E? Yes. E to D? Yes. And D to A? Yes. So this is a circuit. Yes? Yes. But is it an Euler circuit? No, why not? Yeah, it missed a whole bunch of edges, right? Correct. So we started and stopped at the same spot, but it missed a whole bunch of edges. Oh, look, there's my next screen. I told you it was there. All right, so this is not an Euler circuit. You might write a note to yourself that it is a circuit, just to remind yourself that you can tell of that information too. And of course, as you said, it's because it misses or doesn't cross or whatever some edges. There's some that do not happen. Alrighty then, the second one, A to B to C to D to E to F to G. Before I even look at my graph, is this a circuit? No. It isn't a circuit for lots of reasons, but just looking, without even the graph looking at it, how do you know it's not a circuit? It doesn't go back to A. Okay, so it's definitely not a circuit for that reason. But this one has other issues as well. What do you notice? B didn't go to C, and C doesn't go to D. D goes to E, that one's fine, and E to F, and F to G. Those pieces are okay, but it's not even a walk, right? A walk actually means that you have connecting edges between what it says you should be able to get there. I would have to walk off to get there. Yes, Mark?
Okay, I'm just trying to understand, so if it's an Euler circuit, it would use every single edge?
Yes,
so
it would.
in essence, it would also have to use every single vertex.
Of course. More than once, in fact, on most of them. Yeah. Yes, Kristen?
With these ones, it still has to come back to the same point?
For an Euler circuit, yes. Now, we're going to do an Euler path later on, and it wouldn't have to come back to the same point for that one. But for these, yes, circuit means you come back to the same point. So part B fails miserably. So first, it's not a circuit. And that's simply because it doesn't start and end at the same spot. So it starts and ends at different vertices. But this one's also just not a walk, right? Remember, a walk means you should be able to get from one point to the next as it describes it along an edge. And we don't have that on every edge that it's sort of supposing that we did. So could I get from A to B if it wasn't connected by an edge? Not with graphs, right? If I'm talking about sidewalks, I would have to walk on the grass. Agreed? And we're trying to stay on the sidewalks, right? All those signs keep off the grass, kind of an idea in our mind going on, okay? So this one's not even a walk because A and B, and then also B and C.
Wait, I thought.
Oh, was it B and C and D? You're right. Thank you. All right. All right, let's fix that because B and C and C and D are not connected by an edge.
Do we have to give every example, or can we just give one?
You just have to come up with one reason that it fails. This one also fails to be a circuit. If I drew G arrow A at the end, it still wouldn't be a circuit, right? Because a circuit actually requires that it's a walk. So it fails all sorts of things, and you can list any one of them that you want. If it asked for more, you could list more. But yes, Mark?
You only have to list like one reason.
Yes, and that's what Adam was asking. Yes, one reason is sufficient. But keep in mind that you're looking for all of those reasons because you don't know what's going to fail in the particular graphs you're looking at. So that's why I'm being sort of more comprehensive right now. But yes, you only need to list one. All right, so we've got one more example. And I'm going to try and see if I can copy this to the other side of my other screen. Let's try it again. Of course, it's copied some of it, not all of it. Erasers work too. Look at things disappear. All right. This is my supposed circuit, and I got to see if it really works. It looks right on my screen. Oh, there it goes. All right. We're following this along, and we want to see, first of all, we've got the issue of is it a path, right? Is it a walk even? And does it actually end up back where we started with? Does it not cross over anything twice? What's wrong? Did I mess something up?
So, the walk theory for this example.
Yeah. So we're going to have to take a look, right? So does A go to B?
Yes.
Does B go to E?
Yes.
E to F?
Yes.
F to G?
Yes.
G to E?
Yes.
E to D? D to A to E? E to C? And C to A?
Sure did.
Did it work?
Yeah.
Did I cross everything?
You did.
I think I did. Yeah, I think it worked. All right, so this one, which is actually example C, this one works. This one's an Euler circuit.
But I thought you said
Oh, did I screw something up? What happened?
A circuit, like a path can't
cross B 3
cross
times.
any repeated.
It's not the vertex, it's the edge. Did I cross an edge repeated times, or did I just hit a vertex repeated times?
Vertex.
A vertex. That's a great question. I'm glad you asked, because that's a good distinction to make, right? I can go through a vertex multiple times, but I can't cross over the path multiple times, right? So this is like the idea that I've got an office on campus. Some of you have seen me in my office before. Some of you have no idea where it is, so that's all right. But I come back multiple times during the day to my office. But every class that I teach in on Monday, Wednesday, Friday versus Tuesday, Thursday, whatever, depending on which day it is in a different classroom. So I don't really cross any of the same sidewalks twice. So that would actually make something be a circuit, but it wouldn't actually have the issue because, yes, I'm coming back to the same location, but I'm not crossing the same sidewalk. Kind of an idea, okay? So this one works. This one is an Euler circuit.
Will there always be more than one Euler circuit, like in the graph?
There's usually more than one way to do it. And if you can imagine, I mean, we bounced around all over this thing, but could we have bounced around in a different order? Yeah, most of the time you have more than one choice. And in fact, the directions, when we get to drawing ones ourselves or describing ones ourselves, will indicate that there's often more than one choice or one way to do it, which makes grading so much fun, Tyler. It does. All right, let's take a look. Euler's theorem now. Euler, he's an important guy today. Suppose we have a connected graph. Somebody tell me, what is a connected graph? Right. It means that we can go from every vertex to every other vertex along edges, right? I don't have to, in other words, I don't have to go off of the sidewalk to get there. I can cross through the edges and I can get there from one place to the next. So if we have a connected graph, then the graph will have an Euler circuit. If the graph has an Euler circuit, then every vertex has even degree. And vice versa. If every vertex has an even degree, then it has an Euler circuit. Because I don't know about you, but it really bugs me when questions say something like this. Find one if it exists. Because I'm working two angles at the same time. I'm working the angle of what if it does exist, then I need to find one, and I'm working the other angle back in the niggling in the back of my mind saying, it may not even exist. You may be looking for something that's not real. It's not going to work. This is a great theorem because this tells you when it's going to happen and when it won't. All right, we're going to take a look at an example. We have example 2, and the directions say the following. Use Euler's theorem, that's the thing you just wrote down with the two different directions of the argument, to decide whether the graph has an Euler circuit. Notice what it says in parentheses. You don't need to find the circuit. Okay, so don't do more than you're asked to do in the problem. Some of you are really good at that too. I know I am as well. So be careful you're actually doing what the directions tell you to do. And then it says to justify your answer briefly. So, does this graph have an Euler circuit?
No.
Why not, Tyler?
He has 4.
Has 4 what?
They don't all have an even degree.
So they don't all have an even degree. And the 4 you're referring to is there are 4 vertices actually that don't have an even degree, right? So let's write the vertex, beside each vertex, its degree, just to remind ourselves how that works. This is an example kind of like the one that Laura did at the beginning, had us do at the beginning. What's the degree on A? 3. The degree on D? C? B? And E? Well, hey, there's one of them with even degree. That's not going to be enough, right? So this one does not have, well, let's say it that way. No Euler circuit. Because points A, B, C, and D all have odd degree. It almost sounded like something out of a children's book. It was rhymey. And that's all you have to do. And that's great, because if you were being told that you needed to find one or see if one exists or whatever, you'd actually have to try some and see if it works. And eventually you would figure out and decide, hopefully, that it didn't work. But this gives you a way without having to actually try some to see if it works. Okay. We're going to use Euler's theorem in another example. This one's weird because the directions are so long it's not on the same page as the problem. But use Euler's theorem to determine whether the graph has an Euler circuit, just like the question we just had, right? Then we've got an extra sort of condition. It says, then determine whether the graph has a circuit that visits each vertex exactly once, except that it returns to its starting vertex. If so, write down the circuit, and then we see that parentheses, Tyler, that says there may be more than one correct answer. You'll see this multiple times during your homeworks assignment. All right, so we've got two things to do. First thing here is to use Euler's theorem to determine if it has an Euler circuit. That's thing number one. And then thing number two, which we haven't done yet, has this extra condition asking us whether or not we can do this without repeating visits to my office, right? If I can go all the way around campus and not go back to my office, in other words. All right, so we're going to take a look. Our graph looks like a bow tie, sort of. So first question is, does it have an Euler circuit?
Yes.
Yes. Why?
Each vertex has a number.
Yes. In fact, the two outer vertexes on each side, the outer vertices on each side, both have degree, or all four have degree 2, and the inside vertex has degree 4. So we're all good. It has an Euler circuit. So that's thing number one. So first issue, yes, there's an Euler circuit, because all vertices have even degree. Okay, number two, though, was this question of whether or not, if I pick starting at whatever vertex, it didn't even tell me what vertex I have to start at, but whether there is a vertex I can start at, and I won't cross through any other vertex twice before I come back to where I began.
Yes.
So Emily's saying no. Tyler's saying no. Why no?
Because I at least twice.
All right, so if I start at either G, H, J, or K, then I will cross through I twice, right? I'll cross through going in, and I'll cross through coming back. In fact, yeah.
Even if you started at I.
Now, if I start at I, what happens?
You still have to go back to I.
I still have to go back through I. Now, it's perfectly fine to end at I, but that's not what the directions actually said. It said that I'm only supposed to start and end at the letter. I'm not supposed to cross through it in the middle of my walking around campus kind of issue again, too. Yes, Mark?
What, okay, hold on, tell me, I'm confused, why isn't it?
It's an Euler circuit, but it doesn't have the additional feature that if I try to do the circuit, any circuit that I make, I will cross through I twice in the middle of working. Even if I start at I will cross through in the middle of working once before I come back to I at the end. And the reason that's happening is because what's the degree of I? 4. So every time I go in, I have to come back out, which means I'm going to have to go into I, stop at I, and come back out twice. And otherwise, I'm not going to be able to hit all those edges. So what would it take? How could I actually make this problem work? I mean, not this particular graph, but the directions. What would have to happen?
Does every vertex need to have the same even number?
Not even just the same even number, but an even number of 2. I'd have to have every vertex having a degree of 2 for this to work. I start here and I end here. I go into the point and I come back out of that point.
So only a square.
So the only way that would work is if I had, a square or triangle would work, wouldn't it? Yeah. So this one is a no. I promise we're packing up. So no way of doing part 2, or in other words, because we end up crossing through I At least twice.
Maybe so.
Right? At least one more time than I'm allowed to. All right.